Hello everybody, it's Sunday again, and it's time to get back to basics. Today we're going to talk about resistors. Now, everybody that's seen a sci-fi show has probably seen a resistor of some sort. Anybody who uh, is an electronics hobbyist like myself has hundreds, if not thousands of these things, and they look just like this. Get the right look layer there. Little metal leads with a sort of a beigeish brown little lump, or in some cases blue, like in the case of this guy right here. And you put them into your circuits when you desire to control current in certain sections of your circuit. Now you can use these anywhere from just basic current limiting for an LED flashlight to complicated arrays of LEDs that are used for biasing transistors in audio, or I said LEDs, didn't I? Complicated arrays of resistors for biasing transistors in audio applications, precision current measurement, all sorts of different things. But its basic purpose is just to control the flow of current through your circuit. Now, at its very basic first, resistors looked something like this inside. You'd have a lead coming along, and then there'd be a little metal cup, and then there'd be a bar of goo put in there, and then there'd be another cup, and then there'd be the lead, and then they'd cover that with the little ceramic coating that we normally see on a resistor. That's a terrible drawing, but I'm not good at drawing. I'm just here to explain stuff. And you get the point there. So, what's in this bar? Well, originally, that bar was just a piece of ceramic material that had been mixed with little dots of carbon all throughout it. Little tiny pieces of carbon just spattered about all over on the inside. And they were mixed to such a degree that they'd always be touching each other, and you'd have a constant current path somewhere through that resistor, and then it would flow through. And by increasing or decreasing the size of those particles or the amount of them, you could roughly control the value of the resistor. Now, resistors that were done like this were terribly inaccurate. I think the highest accuracy you could hope to get was about 5%, but more commonly 10%. Now, technology has improved for the making of resistors, and now we've got carbon film resistors like these guys, or metal film resistors, which typically are blue, but you'll see the brown ones. These ones are specifically carbon film. And the way they work, and I have a sort of an example here, is you take a tube, or not a tube necessarily, but a cylinder of some insulating material, generally ceramic, and you cover that tube with, in the case of a carbon film, a fine coating of carbon-based polymer, and in the case of metal film resistors, a metal film containing nickel cadmium and some other materials as well. And once you have that cylinder coated, you take a laser, and just like you see on this toilet paper roll, you cut a spiral down that tube, and that interrupts the current path, so that rather than the current path just going straight through, it actually has to travel along that spiral. And the tighter you make that spiral, the higher the resistance is, because the current path is longer. Ah, but Gadget Boy, you say, that looks like an inductor to me. Yes, it will display some inductive qualities at extremely high frequencies. They generally can prevent, well, not prevent, but they can lessen the inductive effect of the metal and carbon film resistors by making the ceramic material that the carbon and metal films are wrapped around have a very low permissivity to magnetic fields, and that will help reduce the inductance of the spiral. And then one other one you see in high current applications are wire wound resistors, and basically I'm just going to grab my multimeter leads to demonstrate this. Give me a second here. They're all tangled up. Oh, sorry, that was a peek on the microphone, sorry. Anyway, so basically you take and you wrap thick wire around a insulative ceramic core, and that allows you to have very, very high power resistors. Now, your basic wire wound resistor that's just this is going to have a pretty notable inductive effect to it. So the way they fix that is by taking a second wire and wrapping it, pardon me as I fumble around here. Oop. I didn't plan this out very well, bear with me. And what they do is they, oops, I did this completely wrong. I'm supposed to be demonstrating this, and I'm not doing a very good job of it. But that's half the fun here. Anyway, so there we go. They take another wire and wrap it in the opposite direction, like, no, I did that wrong again. Okay, let's start over. So, they take the wire, and they wrap one in one direction, like this. So that's going in that direction. And then we want the other one to go not in that direction, but this direction. So I will attempt to demonstrate this. Bollocks. Okay. Okay, well, this wire is really being difficult, but you get the point. You wrap it in the opposite direction. And the reason why you wrap that in the opposite direction is that the magnetic fields that are generated by the current flowing through the one wire are going to be canceled out by the magnetic fields being generated by the wire going in the opposite direction. If you do the exact same amount of turns in one direction and the other direction, it completely cancels out any inductive qualities of that wire wound resistor. And again, they'll make sure that the core of the wire wound resistor is a material that has a very low magnetic permissivity. And we'll talk about magnetic permissivity when we talk about inductors in a later video. And that pretty much negates any sort of inductive effect of a wire wound resistor. Now, I just wanted to sort of give a practical demonstration here with another toilet paper tube that I put together. And we're going to have a quick look. Actually, I'm just going to move this out of the way. And make sure we're still focused down. Bear with me. There we go. Alright, so we're going to set this to ohms, and we're going to clip it on here, and then we're going to clip it on over here. And we're going to have insufficient ohms for my meter to read. Well, there we go. 0.1 ohm. We'll go with that. So, that's just that. But underneath, I prepared one previously. I simulated the spiral cut that you would see in the wire and carbon film resistors. And let's see if we get a different result. I'm hoping we do, because I haven't actually tested this off of camera, which I probably should have. But this just makes it more interesting. Alright, so let's see what the multimeter says now. Ah, it says, well, it went up to about 0.4 ohms there, but Yeah, my multimeter really isn't sensitive enough to demonstrate this, I guess. There we go, 0.3 ohms. 2, 3. So basically, I doubled the resistance by cutting that groove in so that it made the current path longer. But yeah, that's basically about it. There's nothing too super complicated about resistors. Hopefully in the future I'll have a video where I actually demonstrate some actual resistors. I'm setting some things in motion for that. But I did want to say thank you to a company called Ryden, or Reedon, R-I-E-D-O-N. I'll throw a card up right over here. They have a fantastic little PDF guide called The Ultimate Guide to Resistors that I got some of the information for this video from. The PDF guide is completely free. It's available on their website. So just a quick shout out to them, thanking them for that. Yeah, if you haven't subscribed already, consider clicking here, right here, to subscribe. Hit the bell icon if you want to get notifications of new videos. Right over here, I'll put a video that YouTube thinks that you'll like based on your watching habits. Over here will be the Back to Basics playlist. I'm losing the ability to talk. It's time to wrap this video up. And right here will be a link to my Patreon in case you decide you'd like to support me with a couple of dollars a month to help me buy things to do stuff on the channel. So thanks so much for watching, and we will see you next week. Bye-bye.